Today we're going to talk about some more final exam problems, and we'll start with this double integral problem. Here you're given a double integral from 0 to 2, and then from x squared to 2 root 2x of f of xy dy dx. And we're going to do the typical stuff. We're going to sketch the region. I want you to use that sketch to reverse the order of integration. So rewrite it as a dx dy integral, and then calculate the area of the region. That will include show your calculations, and I can't remember if I wanted the exact value. I'll probably put the exact value just because they're fluid. Calculate the area of the region by calculating one of these double integrals, or by making up your own single integral and calculating that. Your single integral actually would just be the middle step of calculating one of these double integrals. So that's the interesting part about these double integral problems. But there's no requirement that you notice that. Any questions on problem number 4? Everybody okay? Nice and straightforward. Draw a picture, reverse the order, calculate the area. So let's let W be the solid cone bounded by z equal this cone. 2 square roots of x squared plus y squared, and on top z equals 2. So I've got this cone. The cone part is z equals 2 square roots of x squared plus y squared. And the flat top is going to be at z equals 2. We want to write a triple integral for the volume of the cone. And I would like a triple integral for the volume of the cone in rectangular coordinates, cylindrical coordinates, and spherical coordinates. One of them is easiest, one of them is best. There's one that's going to be in the middle, kind of a second best, and one that doesn't really make a lot of sense to use, but we're going to use them anyway because it's good training. So write a triple integral for the volume of the cone in the three kinds of coordinates. Next part. Suppose that the density at any point in the cone is equal to the z-coordinate of that point. I shouldn't say z-coordinate of the above the point. I should say the height above the xy plane. Because I'd ask for spherical coordinates and there's no z there. So we have variable density starting at density 0 at the tip of the cone on the xy plane and increasing to a density of 2 when z is equal to 2. Find the mass of the cone. So set up a triple integral to find the mass of the cone, then find the mass of the cone. You can use whatever coordinates work best for you. If you like the cylindrical coordinates, do that. If you like the spherical coordinates because you like to make your life difficult, by all means. I don't know if there's extra credit for doing the problem, the mass problem in spherical coordinates, because I've never had someone actually try to answer the problem in spherical coordinates. Everybody just always just defaults to the cylindrical coordinates or the rectangular coordinates, whichever is easiest of those, which is the smart play. No one ever tries to flex and say, I'm going to do the problem in spherical coordinates. So I don't know if I might call, boom, yeah, extra points. I don't know if that would happen because no one's ever done it. You know what I mean? Even though I've mentioned, I don't even know if there's extra credit for doing it in spherical coordinates, even though it would be messier. So that means pick the best one for you and just do that. Doing all three would kind of be a good idea because you'd be able to find out that your mass is correct. So rectangular and cylindrical, not really so bad for this particular mass. Spherical is a little bit messier. I don't know if it would be worth extra credit because no one's ever done it. So I've never been like, oh, extra credit. You know what I mean? No one's ever done it and I've been like, all right, inspiration. You can have advantage on some D20 roll in the future. Good question. Comment? Live in the back. Originally, there was going to be 3 of each of the different kinds of problems, but once I dropped the spherical coordinates, I was thinking about it. I thought, spherical coordinates, maybe, and then I put that on there. I thought, maybe that will save us from one whole extra problem. It's not even that difficult, but it's messier. So I'm only going to give you 2 multiple integral problems. One of them covering our different coordinates, and the other one just a nice simple double integral sketch of region. Questions? Clearly the theme here is multiple integrals. Yesterday the theme was fundamental theorem of calculus, vector calculus edition, and here we've got some multiple integrals. How's everyone okay? Does anybody actually finish any of the problems from yesterday? How do you decide? It's too early to be thinking about final exams. But then again, it's also never too early to think about final exams. So we've had 3 problems from vector calculus, not 3, but 2 problems from multiple integrals. So we should predict tomorrow we're going to be talking about problems with derivatives. Derivatives involves things like optimization. So expect to take some first derivatives, set them equal to 0 and solve. And if we're feeling like having some spicy problems, maybe a Lagrange multiplier problem. Questions? Comments? Sniper mark. Hasn't gotten us to the essay portion of these yet. I know it's a math class. You're like, oh, wait, what? No, we're not supposed to write essays. But I'm trying to figure out what would be a good short answer where you actually have to write and explain things. All right. So I've only got these 2 problems for you from our list of final exam problems for today. Unless there are no other questions, that's going to do it for today. I'll see you all on tomorrow. I know tomorrow's Friday, but because Tuesday happens, we have to meet on Friday. So that's going to do it for today. I'll see y'all on tomorrow for some more problems. Everybody have a good day, and thanks for playing.